This Hamiltonian consists of multiple terms. For example, this first term, here I and j are the indices of the sites. The first term represents the hopping of the boson from one site to its nearby site. The second term, this u represents an interaction. This term represents the interaction strength of the bosons at the same site. Say if there's only 0 boson or 1 boson at the site, this term is 0. There's no interaction. But if there will be 2 bosons at the site, then this is equal to 1. So it represents the interaction. And the last term is something that we can easily use to tune the number of bosons. So this is the Hamiltonian of the Boson-Hubbard model. Yeah.
What is HC?
What is what?
HC in the interspersed.
Oh, Hermitian conjugate. HC stands for Hermitian conjugates. Yeah.
In the summation, where you put the, I don't know,
Here? Oh, this symbol, these brackets mean that I and J are nearest neighbors. They don't have to be nearest neighbors. For simplicity, we can consider nearest neighbors. Then you can check, this is a symmetry where Q is the total particle number. Because as you can see, if I using the previous logic, if we apply this unitary operator to this Hamiltonian, you will see those terms just don't change. So this is a symmetry. I want to emphasize the total particle number is conserved, but the individual particle number at each site is not conserved. This should be reasonable because afterward, the bosons can hop between different sites. So the number of bosons at each site should not be conserved, but the total number of bosons is conserved. Question about this example?
Yeah. Why do we need to conserve the total boson number, or is that just a setup for this experiment? Because I think you talked before in an earlier lecture about the total, I think this is with fermions, but the fact that we don't actually need to conserve fermion number is totally parity. So why in this experiment for this situation?
It just happens here. It doesn't have to be conserved. Other questions? Usually a symmetry doesn't have to be a symmetry. It's a symmetry, if there's a symmetry, it's just a symmetry there. In principle, we can break it. But break it meaning making a lot of symmetry. Okay, the second example is also the Hubbard model, but it belongs to not bosons but fermions, the Fermi-Hubbard model. Then it has a lot more continuous symmetries. The model looks very similar, you see. Both of them have 3 terms. So this term, again, represents the hopping of the fermions in the nearby sites. Here, I and J are the indices of the sites, and the sigma being up or down represents the 2 spin components. So here, this hopping doesn't change the spin. Spin up hops to a spin up fermion in the nearby site, and spin down becomes a spin down fermion in the nearby site. And this interaction takes this particular form. You see, this particular form is kind of strange, right? It seems up and down, their reputations are not that symmetric, but their reputations are symmetric. This interaction means, for fermions at each site, we can have at most 1 spin up fermion, and at most 1 spin down fermion. Only if both of them have 1 fermion here, there's this interaction. If one of them just has 0 fermion, of course there's no such interaction. And then the last term is something that we can use to tune the number of fermions. I need to emphasize, actually, not only the last term, tuning the other 2 terms tuning the coefficients of this T and the U, we can also tune the average particle number. So in this Hamiltonian, there are many symmetries. One is this total particle number is conserved, it makes.
I'm sorry, Eric, don't know what tuning the number of strings means.
Tuning the number of fermions.
Yes.
So this is the Hamiltonian. Then if you solve for the ground state, you will see the ground state has a particular number of fermions. By tuning these coefficients, the number of fermions in the ground state will be different. That's what I mean by tuning the number of fermions.
Thank you.
So this model is believed but not proved, and actually under very hot debate that is related to the phenomena of the so-called high temperature superconductivity. This is a phase diagram of a high temperature superconductor, a particular type of high temperature superconductor known as the copper oxide high temperature superconductor. It's a very complicated phase diagram, and there's evidence that this Harvard model has something to do with this phenomena here, but this is under very hot debate. And here is a crystal structure of the high temperature superconductor. Essentially, the active player of the high temperature superconductivity are these copper atoms, the yellow or brown, a little bit red color, these ones. The electrons are basically moving around on these sides. And people think this model may be relevant to this phenomenon. Yeah.
Sorry, what is sigma under the subscript?
The spin component, up or down, spin component.
It's different from the other down.
Here?
Yeah.
Not different.
They're different, right?
Not different.
They're the same.
Yeah. I missed the summation of sigma here. Sigma should also be summed here.
Okay. Second question, which is given the Hamiltonian, how do people know that there exists symmetry like 1, 2, 3, 4? Is this something that they can tell from the equation, or is it that they?
Yeah. Yeah. So the question is, given a Hamiltonian, how do we check all the symmetries, right?
How do you know that there exists a symmetry operation U1?
Yeah, for U1, you see this, we have intuition because you know this Hamiltonian, you see every process is just at most some fermions moving around and they interact, but the total number of fermions doesn't change.
Okay, what about U2?
Let me finish U1. The total number of fermions doesn't change. It means this is a conserved quantity, and it will generate a U1. It will generate this U1 symmetry. Very interestingly, this symmetry has a general name called a U1 symmetry. So how do people know there are 3 other symmetries, right? That's your exercise here. Verify that. But let me answer I will verify this for you. This requires a trick. Let me answer your other question, maybe the more general question. Given a Hamiltonian, how do we know all the symmetries of this Hamiltonian? There's no systematic way of knowing that.
So there could be more here.
There can be more symmetries of this. If you can find one, you can write a very impressive paper. It will be significant for this particular model. In the past history, some of the important development was to identify some symmetries in some models. And one of my paper was about 2023. There was a debate. There was a puzzle in the field. Then just by finding out a symmetry in the Hamiltonian, then we were able to provide a very simple explanation of the debate. It's a very simple and nice work that I like. Okay, so now let me explain why the other 3 are the symmetries. This is something that if you didn't see before, you will find it a bit surprising, but after seeing it, you should be familiar with it. Of course, the most straightforward way to check that these are the symmetries is just to use the definition to check whether these operators commute with the Hamiltonian. But that's a bit tedious. Let's look at the simpler method. First, let me claim. In fact, let's consider a generic unitary operator. Let me write it in this form. Exponential of I theta So here this sigma is the Pauli matrices as matrices, not as operators in the physical states, just as matrices, 2 by 2 matrices. And the sigma alpha beta is the matrix elements of these matrices. And n is a generic, it's just some unit vector. Then I claim this will be equal to this. So let me first explain the meaning of this statement. So the left-hand side is the operation of the unitary on this operator. If you want, you can put dagger either here or there. This will change the V, but eventually it will not change the fact that it's a symmetry. This is the left-hand side. The dagger, you can put it either here or here. That will change the V. And this V is some matrix, is some 2 by 2 matrix. And as a matrix, this V is just this matrix, I think, or there's a minus sign, one of them. Then let me check which one it is. The reason that this is true is because we can look at what this is, right? I can look at this in 2 different ways. I can first write it as this one. I'm just inserting a UU dagger here, it's just equal to identity. Now I look at this part and look at this part. This part is just still the vacuum state because I'm operating, I'm doing some operation, but the vacuum doesn't have anything for me to do the operation. You can also check by definition of U, because U has an F in the right, so if you act on the vacuum, it just gives me 0. That's why it still gives me, now it's in the exponential, that's why it still gives me the vacuum. On the other hand, I can also look at this quantity, this left-hand side in another way. This is saying I have a particle at set I with spin alpha. And the U dagger is just, as we saw in week 1 and also multiple times in assignment 4, U dagger acting in such a state will just rotate the direction of the spin, right? So the rotation of the direction of the spin will be given by some 2 by 2 matrix for spin 1/2. Therefore, the left-hand side can be read. There must be a 2x2 matrix with such that the left-hand side is takes this form. Now we just strip off the vacuum, and we will see this equation is true. There's this kind of 2x2 matrix. Is this clear? So the meaning of this is the action of the unitary operator on this operator can be, the result is some linear superposition, and this linear superposition can be organized into this form of a matrix acting on this operator. Yeah.
Yeah, so I want to ask, when you say that the Ohio dagger is that and it rotates the speed, this statement comes from
Qubits.
no, let's see. Because on the previous question we do let's say EIJZ against the JN, just now I asked for physical meaning of rotation. It seems that that the idea of rotation of the spin doesn't come from maybe just applying the exponential term.
It does. It's just that the particular question you asked before that is kind of the special case where there's no rotation.
Okay.
It only multiplies a phase. But in general, if the angular momentum is pointing in this direction and the spin is pointing in that direction, there will be rotation.
And
The example you were asking is the angular momentum is in this direction, the state is in this direction, then there's no rotation.
so in that example, we can do that by exponential.
Yeah.
Okay.
We kind of did this in week 1. Okay, so knowing this, then it becomes very simple. Then, for example, if I want to check that this is invariant on this, then we will just notice that this term is also equal to this thing is also equal to this, right? And then each term, here f dagger will be multiplied by some v. That means f will be multiplied by some v star, right? But we know v is a unitary operator, so after summing over sigma, this will be this one. That's precisely the same as what we had before. Is this argument clear? I'm applying this general set of unitary to the first term, and using the fact that the action on f dagger is this can be translated using this unitary matrix. I see that this term doesn't change. Similar argument can be applied to every term here, and also here you see this kind of unitary covers these 3 cases, depending on the choice of the unit vector. And if n is in the z direction, that is u2. If it's in the x direction, is u3. If it's in the y direction, is u4. So this shows these total angular momenta they are conserved in the Fermi-Hubbard model. Question about this?
Slight question. Is Ni sigma equivalent to F dagger I sigma F I sigma?
Yeah.
Okay.
Other questions? Okay. Then the next example is the Eisen model. So it's a model of qubits, and the Hamiltonian takes this form. This is a cartoon picture of the atom model. It turns out this is a symmetry. If we, for example, if we acted on the Hamiltonian, this and this of course compute, but this U doesn't compute with each individual Z, but we have two Z's together. For each Z, we will have a minus sign. Now we have two Z's, the two minus signs cancel, and this is still a symmetry. It's easy to check if we consider this kind of general symmetry and this kind of operation, where theta can take continuous value, then usually this is not a symmetry, because if we consider this kind of operation, when we act it on this Hamiltonian, although the second term doesn't change, the first term, the Z will become some combination of Z plus Y, right? Because of this picture. This is some rotation around the X direction. It will rotate Z into something that is Z plus Y. So the Hamiltonian will not be the same unless I can just completely flip the Z. So here you can actually check only for some specific theta, this will be a symmetry. Let me quickly go through this part. It's indeed pretty quick. So one application of the symmetry is that it will simplify our analysis of the Hamiltonian, because states in different symmetry sectors are decoupled. Let's consider this example of Bohr-Hubbard model to illustrate this. Here, by symmetry sectors, I mean the subspace spanned by states with different conserved charges. The claim is that the matrix representation of this Hamiltonian can always be written in this block diagonal form. Here, H0 is the Hamiltonian for the vacuum state, H1 is the Hamiltonian for one particle states, H2 is the Hamiltonian for two particle states, and so on and so forth. The important thing is this is block diagonal. There's nothing here, 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 here. If I didn't write anything here, then everywhere is just a 0. Let me explain why this is true. Also, this explanation explains what these individual Hamiltonians are. So, to make it more streamlined, let's define a set of projectors. Let's say the projector onto the vacuum state is just this one. The projector onto the one particle state is just this one. The projector onto the two particle states are just this one, right? The usual definition of projector is just the sum of the orthonormal complete basis of this subspace. Then the reason for the decoupling is as follows. First, we notice if we add up all the projectors together, we should get identity. This is a common property of the projectors. So the Hamiltonian will be equal to this one. Any question about this? Because this is the identity, this is the identity, so the Hamiltonian is equal to this one. The meaning of decoupling is that if M and N are not equal, then in this term, in this summation, this term is 0. The reason is because the following: suppose here, without loss of generality, suppose M is not 0, then here Q is the conserved charge. We know Q times Pn is just N times Pn, right? N is the particle number. And the Pn is the n particle state, therefore this is just N times Pn. Yeah?
Sorry, for projector, what are we signing against?
A complete orthonormal basis of this space, of this subspace.
Also, P1 is not 1.
P1 is not 1 in the entire Fock space. It's 1 in the one particle state space.
Okay.
So as usual, projector is always projector is nothing but an identity in some subspace and 0 in the orthogonal subspace. Okay, so then if we look at this PNH PM, using this equation, this PM can be written as this one. Because M is non-zero, is assumed to be non-zero, this operation is legal. M is in the denominator. Then this equation can also be written here. I'm just moving M there. And then I'm using the assumption that Q and H commute to change QH into HQ. After changing it to HQ, then I use this equation again. QPN is equal to N times PN. So what I obtain is this quantity is equal to this quantity itself times N over M. But N over M is not equal to 1. So this quantity itself is equal to 0. That's why in this summation, many terms are just 0, and what's not 0 is just this one. And this is our HN. This is useful because if we try to understand the spectrum and the dynamics of a system, we may need to diagonalize the entire Hamiltonian on a computer. And the matrix diagonalization, if we have an n by n matrix and we want to diagonalize it, the computational complexity scales as n cubed. So if we don't decompose the Hamiltonian into smaller pieces, then the total complexity of computation will just be this much. But if we do decompose the Hamiltonian into smaller sectors such that we have, say, one part of the Hamiltonian that is n0 by n0, then another smaller Hamiltonian that's n1 by n1, another that's n2 by n2, and so on, then the total complexity will just be this one, right? We just diagonalize the Hamiltonian, each individual Hamiltonian separately, and then add the result together, combine the results together. And when n capital N is large, this quantity is much smaller than n cubed. It will save us a lot of computational power and time. That's why it's useful. And in assignment 6, you will experience that.
So can we go back to the previous slide?
Q is the conserved charge, total particle number. Other questions?
What happens when Q is small? The conserved charge is zero.
0 as an operator?
No, I see. Quantity.
You mean what happens if n is 0? This argument still goes through, right? Here, m is not equal to n, it means m and n cannot be simultaneously 0. One of them has to be non-zero. Let's assume m is non-zero. If n is 0, the argument still goes through. Yeah.
If n is not the total particle number, since it's a generalized the conserved charge, will h be still be diagonalizable?
Yeah. So here, in this particular example, n is q is the total particle number. But you can see this argument applies to any such things, right?
Also, so QPN equals to NPN is not because Q is the total number?
In this example, where n is interpreted as the total particle number, the reason is because q is the total particle number. But in other cases, where q is something else, this n is just interpreted as the eigenvalue of that subspace. And the statement in those cases would be, here the decomposition is not decomposing into different total particle number sectors, but into sectors with a fixed eigenvalue on that particular Q? Good question. Other questions?
So when Q appears means it's continuous.
Huh?
If there's a Q, that means that the symmetry is continuous.
Yeah.
Is it?
Yeah.
So
But this argument can be generalized when it's not continuous. More generally, suppose we have a general unitary operator U, which has multiple eigenvalues, say U1, U2, and so on. We can consider the projector Pn that is the projector into the subspace to the eigenspace with eigenvalue Ui, right? Oh, that with eigenvalue Un, right? Then the same argument still goes through. Nothing changes. Huh? You don't believe it?
no. I'm still trying to process where the Pn. What's the motivation for projector? I thought the Q was communicating with H and not Pn.
I didn't assume it commutes with Pn. I'm using Pn is just a fact that this Hamiltonian can be decomposed in this form where what appears here is Pn.
I need more time.
Okay. That's what I want to talk about today.